So we solve this problem by our experience. We learn. So this is problem number 4. So our experience, we solved 3 computing problems. First one, polynomial evaluation. Second one, linear search. Third one, finding the minimum. So we can use the results from those 3 computing problems. But only the third one is related to this problem. So we build the solution on top of the solution of the third problem, finding the minimum. All right. So then we use the backward thinking. We assume, so here in the general problem solving process, first we need to, when we understand the given problem, we need to really do the good observation. So you need to collect all the information given from the problem. So then connect to your experience and explore the properties in this problem. Explore many properties. Among those properties, there is one that is the most important. So that's the critical property. Critical property. Discover the critical property. So that's the insight. So you need to, catch that insight. Usually that is not easy. So the more experience you have, the better you can discover the critical property. All right. So here, the critical property here is when we make our observation. If we can find the minimum of the current array, we know that element, we can put it in place immediately. The minimum of the current array can be put in place immediately. That's the critical property. If you can discover this property, then the solution is almost there. All right, so here. I need to do here. All right. So we do several iterations. We do the for loop, several iterations. We start from the first element and scan the whole array and find the minimum. Apply our minimum solution. So we get a minimum. That minimum, we know, must be the first element in the destination array. In place. Final, the destination, it is in place. So after first scan, we put the overall minimum in place. Then that element in place is eliminated. Because we do not need to touch that. Already in the destination position. So no need to touch it anymore. Then we can safely remove it from consideration by the elimination method. Then we start over from the beginning after elimination. Okay? We did one elimination. So then we start from the new beginning element. That is the second element. Second position. Okay? Yeah. Then apply the minimum solution another time and get a new element in place. Yeah. So we keep doing that. Every time one element in place, until the last element at the end you reach the last element. When you reach the last element, because when you reach the last element, only one position left in the destination array, right? Then you do not need to do anything. You just put it in place. Okay? Yeah. The reason is this. The reason, another property here I want to mention, because some students may not be able to see this property. So here, let me describe the simple property. Although simple, but I want everyone notice this property. So what's that? Given any array, if we know there are n, so let's say, given any array with n elements, total n elements, if we know n minus 1 of those n elements are in place already, we know n minus 1 of them already in place. What can you say? Yes. Yeah. So the last one is forced in place, right? Yeah. Although this property is so simple, most students can see that immediately. But I noticed one or two small number of students, they couldn't see it. Yeah. So, because later in your homework or quiz questions, I may give you a question derived from this property. Okay, yeah. So at that time, you need to, connect to this property immediately. Then you can get the right answer. Yeah. All right, yeah. So here, so that's what we learned last time. Let's move to the next slide. We do analysis. Let us count how many comparisons do we need to solve. And in this solution, only in this solution. Okay, all right. How to make all elements in place. Here, this diagram. The first time, minimum 0, we use this notation, min 0, the first minimum in place. Second one, second min in place, and so on. Okay? The last one, you don't need to do anything. Yeah, we know. Because only position available for the last element, just put there without doing anything. Yeah. All right. Based on this diagram, now we can calculate number of comparisons. So because we did this many rounds, right? We scanned the array this many times. Yeah. Let's count the number of comparisons each time, each scan. The first scan, how many comparisons we do in the first scan? M, correct. Oh, yeah, let me change the color. Yeah, correct, n minus 1. Yeah. So that's from the solution, finding the minimum, that solution. N minus 1. Yeah, so the first one. Okay, yeah, all right. The first time n minus 1, the second time n minus 2, and next time n minus 3, and so on. Okay, going backward. The second to last time, one comparison. The last time, no comparison, right? The final time, 0 comparison. Add up these consecutive integers by our basic formula. So we know it's 1/2 times n minus 1. Okay, yeah. So here, yeah. One little thing I want to point out, because I noticed one student, look at here. You see 1/2. 1/2 is a fraction. 1/2 times n minus 1 Can you guarantee this expression is always integer? Yeah. Because I saw one student put a floor function or ceiling function around this one because that student does not, make sure this expression must be integer. So put a floor function, ceiling function. Actually, you do not need to put a floor function, ceiling function. Yep. Because 1/2 times n and n minus 1, these two integers, one of them must be an even number, right? Either n or n minus 1 must be an even number, right? Even number times 1/2 must be integer, right? So don't worry, two consecutive integers, n minus 1, they are two consecutive integers. One of the two consecutive integers must be even. So 1/2 times even, always integer. So don't worry, this expression must be integer because it comes from sum of all these integers. How can it be a non-integer number, right? It cannot be a non-integer number. If this formula is correct, it cannot be a non-integer number, right? Yeah. So, Otherwise, you put a redundant floor or ceiling function to make it integer. It's redundant. Okay? Yeah. All right. Then, can you see? So here, let's answer these questions. What is the best case? We know the concept, best case efficiency, worst case efficiency. Can you tell me, to solve this problem in this solution, what is the best case?
It's already in order. Best case would be it's already in order.
Already in order. Yeah. Oh, yeah. He said the best case corresponds to the input array that is already in order. Yeah. Can you tell me, if the input array is already in order, how many comparisons do you need? N minus 1. N minus 1. The first round, n minus 1, you find the minimum, right? Do you need to do the second round? Do you need to do the third round? Even if already, so here, let me tell you. Even the given input array is already in order, but the computer does not have eyes. The computer does not know it. Okay? So do not use your own capability to understand computer. You can see it's in order, but computer cannot see it. Okay? The computer only executes your program. Okay? Your program is written in this way, then even if it's already in order, the computer is just a machine. Machine does things based on instructions. The instruction tells the machine to do step by step, then the computer just follow, no matter what. Okay? With this understanding, how many comparisons, even if the input data is already in order? Can you see that? Computer cannot see it. Okay? Yeah. How does the computer know it's already in order? If your code does not contain any checking steps, right? If you do some checking, then it's possible. But if here, we do not have the checking part, right? Yeah. In our solution, we do not put any checking steps. So if the given array is in order or not, it doesn't matter. Okay, no difference for this particular solution. Okay, not for other solutions. Other solutions, there could be a difference, but this solution, there is no difference. No difference. So the conclusion is, same number of comparison. You need to do finding these minimum, one by one. You cannot miss anyone. After you find all these minimums, you have to use the same number of comparisons. So the best case, still this same formula. The worst case, the same formula. The average case, the same formula. Only one case. Only one case. Best case, worst case, average case, one case. So for this solution, one case. Okay, this solution, one case. Other solutions, we may have many different cases. But this solution, only one case. Okay? Yeah. So that's the analysis. Here, let me do the summary on elimination method. Because later, there are several challenging questions. You need to rely on this elimination method to solve. Okay? Later. Challenging questions. So what's that? The goal, reduce the problem size. Based on our experience, we can see this simple fact. Okay? If the problem size becomes smaller, then the whole problem tends to be easier to solve. If the problem size is smaller. Okay? Yeah? So it's simple to understand this one, right? Yeah. Later I will treat this. Yeah. Reduce the problem size based on one how do we call that? Yeah. Here I like to call that as a principle. Okay. Yeah. If we call fact, it's not as good as principle. It's better to call it a principle. Okay?
What?
Sorry?
Call what as principle?
Call this, the smaller the problem size, the easier the problem can be solved. We call that as the principle. Okay? No. But we do not call that as a fact. Okay? As a principle. So there is small difference. Principle, when we talk about principle, that means this statement is true most of the time, but may not be true 100% of the time. Okay? Most of the time it is true. But there is exceptional cases. Sometimes this statement may not be true. Okay? There are exceptions. Later I will give you the exceptions. If we say it's a fact, then it must be true all the time, right? 100% time, no exception. Okay? Then it's a fact. Okay? It's a fact. Yeah. So we cannot call it. It is a fact, but it's a principle. Most of the time it is correct. But there are exceptions. Later, at appropriate place, I will give you the exceptional case. Yeah. Example, counter examples. So this principle does not hold counter example. Okay? So we call it principle. 99 something percent, it's true. Yeah. So in our problem solving, we can use this principle. Okay? All right. Yeah, so here, I wrote here. Okay? Yeah, so that student asked me, what's the principle? This one. Okay? Yeah, so I don't need to copy it again. The smaller the problem size, the easier the problem. Okay? So we want to make our problem easier. Okay? So we want to reduce the problem size. All right. Yeah. When some elements do not change the outcome. Yeah. After we did some work, at some point, we observe some of the elements will not change the outcome. Okay? Now, after a few steps, some of the elements. So if you include them or exclude them, no difference for the outcome. Yeah. Then we can safely eliminate those elements out of consideration. For example, after you did finding minimum solution, the first scan, then the first element, we know it's already in place. If you include it or exclude it, it does not change the outcome, right? Yeah. It must be in the first location, okay? It does not change the positions for other elements, right? No impact. No impact for this element on other elements, okay? So you can safely eliminate this element here. So that's the essence of the elimination method. If you can find those elements, you should eliminate these elements immediately. Okay? Immediately. Why? Yeah. So here, I based on, later we will do some relatively hard questions. There is experience. Here, let me describe it. If you do not eliminate, because some students, they forget to eliminate, because the problem is relatively hard. Okay, you did some work. Okay, you find some valuable properties. Yeah, you have some valuable properties, but you do not take advantage of those nice properties. Okay. So you do not do the elimination, you still keep some. So even if some of the elements are ready, they don't make any impact on other elements, but you still keep them in the consideration. Then the consequence is you may do some redundant work, because you may do some comparison with those unnecessary. Those elements, you do not need to do anything, right? But you do not know it, or you are not aware of. You're not aware of that. So when you do comparisons, you still do comparisons with those useless elements, okay? You waste your comparisons because the comparison you do on those elements is useless. You won't get any useful information because those elements should be eliminated, okay? But if you are not aware of that elimination thing, you still keep them, it's very likely you do a lot of redundant comparisons. Then your solution will be worse. So that's the consequence if you do not do elimination. Very likely you do redundant work. Okay? Yeah. All right. Yeah. So when we get there, later we will have a question. You see this. Yeah. The question describe this question very short. Yeah. So here I can let you know. Finding the median of 5-element array. Given an array with 5 elements array. How to use the minimum number comparisons to find the median. So this question is very challenging. Okay? You know the median, right? Yeah. Given a 5-element array, if you sort it, there is one in the middle. Let's assume these 5 elements are distinct. They have distinct values. Okay? After you sort it, there is one in the middle, right? The one in the middle we call the median. Median, okay? Yeah, so that's the meaning. So how to use the minimum of comparisons to find the median in the 5-element array. To solve that problem. Yeah. Here you can try, because for your knowledge, you can solve, but extremely challenging. At this point, for you, extremely challenging. Okay? Yeah. If you want to try, you need to prepare, at least you need 4 or 5 hours. Yeah. That hard. But later, I will show you how to use elimination method to solve it. Elimination method to solve it. Yeah. So let's delay it. Yeah. Okay. But at some point, we will work on this one. Yeah. All right. So let's continue. 8.2, impact of organized data. In module 1, we mentioned sometimes we're willing to spend our resource to organize the data. Yeah. How important is that step? Here we can see how important if we spend our resource to organize the data. We call it investment. We make investment in organizing the data. Okay? Yeah. If you can benefit of your investment or not, that's a question. Can you benefit from your investment? And that's a question. So let's consider a new computing problem. Okay, all right. Problem number 5, element uniqueness problem. A simple computing problem. So let me give you the description of this problem. Given an array, this notation, capital A, indices from 0 through n-1, and elements. How to check if all the elements are distinct? Yeah. You only need to do one thing, okay? Checking. Yeah. So write a function. Yeah. Input this array as the input. Okay? So then your function should produce yes or no, or true or false. Yeah. Boolean output. If all the elements are distinct, then true. The function returns the true value, otherwise false value. Okay? Yeah. How to solve this simple computing problem? Very simple, right? Yeah. Okay, very simple. Yeah. Here, yeah, let me mention that some of you may heard of it. Okay, some of you may heard there is one test. Okay, yeah. So in some top tier IT companies, so when they hire new programmers, so they give algorithm test. Anyone heard of that? Some tests. Usually on some company, top level, okay? Yeah. Because they want to select the best problem solvers available in the market, okay? Yeah. How to show people, how to find, so what the programmers, they are better problem solvers, right? Solve algorithm questions. Okay? This is one of them, all right? This is a simple one, yeah, because they rank the difficulty of those problems in different stars. 1 star, 2 star, 3, 4, 5. The hardest questions, 5-star questions. This one, probably 2-star questions. Yeah, not trivial. Yeah. Not 1 star, okay? 1 star is almost trivial questions. Okay? Very simple. So this you can rank as 2-star questions. A little harder than the trivial questions. Okay? All right. Yeah. So let's look at how to solve this question. Uniqueness, element uniqueness questions. All right. Yeah. Yeah. So, in section 2.3, the material comes from there. Yeah. Method 1 here, we use 2 methods to do it. The first method, straightforward method, we call the brute force method. Okay? Straightforward. You do not need to do anything. You start doing comparisons immediately. Do comparisons. Okay? Check if there are any 2 elements with the same value just by comparisons. Okay? That's easy. The brute force method. All right. Do nothing to organize data, because in that way, you do comparison immediately. You do not waste any resource to organize your data. When you organize your data, you need to invest your resource. Here, you do not do that. Okay, all right, no. So the preparation step or data organization step, no cost. You do not do anything, no cost in preparation step. Yeah. So let's do the comparison. Here we assume the array has these values. Suppose this is a sample input like this. How do you do comparison? Yeah. How do you check? Yeah. Brute force. Yeah. First, you want to check if the first element is repeated somewhere. First element, you only check the first element occurs. The value of so here 0. If 0 occurs somewhere at a later position, so you use the first element to do comparison with all the remaining elements, right? Yeah. You need to compare all of the remaining elements. So you need to do n-1 comparisons to see if the first element is duplicated or not with n-1 comparison for the worst case, right? For the worst case. The best case, the second one, the second element has the same value with the first. That's the best case. So one comparison, you can see it is duplicated. But the worst case, you need to compare all the remaining elements. That's n-1 comparisons. How about the second? After you check the first one, then you need to check if the second element 1 is duplicated somewhere in later elements. So you need n-2 comparisons and so on. Yeah. Okay? Do the checking all the way. Okay? Yeah. Yeah. Until you reach the end. Yeah. Next to last, one comparison. The last one, no comparison. Okay? The last one. Nothing to compare. The last one. In this way, you can see what is the worst case of this algorithm. Worst case, not best case. Best case 1, it's too easy. 1, we are done. 1, we are done. The function returns a Boolean value after 1 comparison. That's the best case. Worst case is this one. Yeah, so the best case, this is best case. 1 comparison. The worst case, this one, or the last 2 elements different, still worst case. This is the worst case. Okay? Yeah. Here, let us compare the worst case. Yeah. All right, so let's store this answer. All right, so this is our first method. In our first method, the worst case equals this formula. So let's store this formula temporarily somewhere. Yeah. And let's do the second, method number 2. Method number 2, we solve this problem differently, slightly different. All right. Yeah, for the average case, you can think about it. Okay. Yeah. So at least here you think about it. Yeah. If later I have chance, for example, when we do review, if we have chance, I explain the average case. Here you just think about it. If you need to consider the average case, how do you consider it? All right. You need to connect to our experience. Now, some previous computing problem we learned. Our problem 1, 2, 3, 4. Looking for some related experience in those 4 problems to answer this question, average case efficiency. All right, yeah. Then, pay for some cost to organize data, our method number 2. This time we do things differently. Before we start, we want to invest our resource to organize the data. And we want to see, with this investment, can we improve our overall efficiency? Yeah. So that's the question. Okay? Yeah. All right. Investment in data structure here. All right. Now, what kind of investment? We sort the array first. You need to pay some cost, right? In order to sort the array, you need to pay. Yeah. Pay a resource for ordered data. After the investment, what do you get? You get an ordered array. That's better. Yeah. Before your investment, before you pay this much, you get unordered data. So the difference is ordered data versus unordered data. Yeah. And how much is the cost? Yeah. We will use our later result. We won't use the sorting algorithm of our previous one, selection sort, because that one is very slow. Yeah. That is our first sorting algorithm. It's not a good one. Later we will learn many much better, much faster sorting algorithms. So we will use, so here, so that we use sorting algorithm with this many comparisons, n log n. Later, we will learn several algorithms can give us this efficiency number. Okay? N log n, n times log n. Log base 2. This log, we mean log base 2. Okay? In our computer science, the default log base is 2. Not in math. In math, the default is 10. Okay? Default log base is 10. In our computer science, the default log base is 2. Okay? N times log base 2. The default log base. All right. Yeah. So before we work on our current problem, we pay this much cost. N log n comparisons. That's our investment. After that, we enjoy the nice property derived from this investment. What's the nice property? Order the data. That's the nice property. Okay, so we enjoy that property. All right, now let's do the work. Element uniqueness checking work. Right? Yeah. Here already in, so this array is already in ascending order. Ascending order. Now, if I ask you to check if there is an element that is duplicated or not, how do you do the checking? Think about if there are two elements with the same value, how do you find those two elements? Correct. That observation is the key. So what's that? Only compare two adjacent elements, right? Two adjacent elements, right? You do not need to skip, right? Yeah, because if there are two elements with the same value, there must be two adjacent elements with the same value, right? After it's sorted. Can you see this simple fact? Can you see a simple fact? In order, if two elements have the same value, usually there is a block of elements, right? Consecutive locations with same element, same value, right? Yeah. So then two adjacent elements must have the same value. So when you do comparison, you only need to do adjacent comparison, right? Adjacent comparison. Can you see if you only need to do adjacent comparison, you can do much less work, right? Much less work. The previous one, you need to do global comparisons, right? Global. Here, we only do local comparisons. So you change your work from the global work to local work. Which one is better? Okay? Local work. Yeah. Tell me, how many comparisons you need for the worst case? In this case, this situation. For the worst case, how many comparisons do you need? N minus 1. Yeah, Justin. Exactly. N minus 1. Because you can only find N minus 1 adjacent pairs, right? N minus 1 adjacent pairs. Can you see that? Yeah. Not N adjacent pairs. N minus 1 adjacent pairs. Yeah. That's why you only need to do N minus 1 adjacent comparisons. Okay? Yeah. If you write a code, one simple for loop like this. Okay? If two adjacent elements are equal, return true. Or return false. Because false means duplicated. Okay? Not distinct. Not distinct. That's false. No. Otherwise, if you complete this for loop, still you do not return false value, then the value must be true. No duplicate value. So the function must return true. Okay? See? Our method 2, yeah. You put a lot of, that's the investment. That's quite a lot. That's quite a lot. Okay? N log n. All right? Yeah. But you enjoy the result, you reduce. Remember the previous solution, the number of comparisons reduced to n minus 1. That's quite significant, right? Quite significant. Yeah. But your final total cost, you need to include the investment part. Because you already paid that much. Okay? Out of your pocket. You already paid it. Yeah. So you cannot ignore that cost. We need to include that. So your total cost adding together, these two parts, adding together, that's your total cost of method 2. Now we need to compare the difference between method 1 and method 2. So our next step, we need to compare, is the method 1 better or method 2 better? So we answer this question in part B of module 2. So we complete part A. At this point, we complete part A. Next, we move to part B to compare these two methods. Which one is really better eventually better. Okay? Especially where n is very large. Especially where n is very large. Yeah. Because I mentioned before, usually we do not worry about the situation when n is relatively small. Yeah. Why? We know our computing resource is very powerful. Okay? Yeah. So our computing resource, very powerful. So for n relatively small, we don't worry. So we can find a solution quickly. Yeah. But the harder part is where n number is very large, super large, then we worry. Yeah. Because we don't want to spend days or months or years to find the computing result, right? You don't want to spend years to find computing result, right? So we worry about that. That could happen. That could happen. Okay? Well, if your algorithm is not good, when n is very large, that could happen. Okay? All right, so let's move to part B. Topic, growth functions. Growth functions. A new concept. In order to study the efficiency, so if we look at how fast is the algorithm, we want to use a special function to describe our algorithm. So we call it as a growth function. Yeah, I will give you some examples. So what's the growth function? Okay. All right. B.1 introduced growth function, this concept. So let's look at the simple concept. All right. Formula between running time and number of basic operations. So here, I want to do one important work here. So here I do preparation, give you introduction. So what kind of work I'm going to do here? Do characterization on our algorithms based on their efficiency functions. We know each algorithm should have some efficiency function. Yeah. So now we want to do characterization, put them into different categories. Yeah. The question is, how do we do the characterization? How we put them in different categories? Yeah. So that's the goal. Okay? So here we do the preparation. In order to get appropriate categories.
Are we categorizing them, is it problems or
Algorithms. Yeah, algorithms. Based on algorithms. Okay? Yeah. So because the problem could have different solutions, right? Each solution has one algorithm. Yeah. Some algorithm is good, some algorithm is bad. So we only look at the algorithm, okay? The efficiency function of the algorithm. So the same problem, you have many solutions. Yeah. So we do not characterize the problem, we characterize the algorithms, okay? Yeah. All right. Notations first. First, to study the running time function, we use capital T. Capital T of n. N is the problem size, okay? Here you just understand the number of elements in the array, the problem size, okay? Yeah. If you execute a certain algorithm, you want to measure the running time function, capital T of n, running time function, okay? But when you talk about running time, you need to specify the machine first, right? Yeah. Otherwise, because for different machines, the running time could be different. Here, let us assume we're working on a particular machine. So there is one machine here, okay? So we're working in one particular machine. Yeah. So we do not compare different machines. So we only do our comparison in one machine. this running time function. Then another function, we count the number of basic operation, capital C of n. That's the number of basic operations. So we want to look at the relationship between T of n and the capital C of n. What's the relationship between them? Yeah. There must be some relationship. Okay, now, so let's find that first. So what's the basic operation? Let's recall, I mentioned once before, the operation contributing the most to the total running time. Yeah, basic operations. Yeah. For example, the multiplication in our polynomial evaluation problem, that's the basic operation, contribute the most. Yeah. In later, a few questions, comparisons, the basic operations. Yeah. Element comparisons, yeah. Basic operations. All right. Then we make assume the execution time of one basic operation in our current machine, some specific machine is chosen. There is one machine. In that machine, the execution time for one basic operation is little c up, sub up, little c. This is a constant. On a fixed machine, we can assume this constant. Okay? Yeah. We can assume this constant. Yeah. All right? Yeah. It's fair. It's a fair assumption. Reasonable assumption, at least. Okay? All right. Then, how do you establish relationship between capital T of n and capital C of n? The formulas. We have a simple formula to connect those two functions. Yeah. Here we need to take approximation approach. Capital T of n approximately equal to little c of times capital C of n. Approximately equal. We cannot say exactly equal, not because a lot of things that can change the values. A lot of things can change the values. So we do not require the equality is exact. No. Approximately equal, good enough. So here we need to use that approximation understanding. Yeah. All right, yeah. So now we need to see from this formula. So we want to get some conclusion. Interesting observation from this formula. Yeah. These two functions are proportional, right? Yeah, proportional. Okay? Yeah. With a fixed constant, little c. Proportional. Yeah. For example, if you double c function, if the c function value is doubled, then t function is also doubled. So that's what we mean, proportional. Okay? So if you triple the c function, you also triple the t function. That's the proportional relationship. Okay? All right. Yeah. All right. But with this, so here you have two functions, related functions. Yeah. Yeah. But last time I mentioned the c function, we use a number of basic operations. It's a stable measure for algorithm efficiency. But t function is not a stable measure. Okay? Not a stable measure. It relies on machine, different machine. C function does not rely on machine. So it's a better, stable measure. So that's what we learned last time, before. But one stable measure, one unstable measure, they're related with in this formula. That's the relationship. Okay? Yeah. All right. All right. Here, Remember, we want to do characterization on algorithms, right? Yeah. When we do that, we ignore unnecessary details. Some details is not that important. So we need to simplify the situation by ignoring some unnecessary details. Yeah, so that's what we are going to do. Okay? Yeah. All right. Can we ignore some constant? Yeah, so here, in our formulas, we will have many different constants. Yeah. So how do we deal with those constants? So here we need to look at that question. Yeah. All right. Can we ignore some minor terms? Remember last time I talked about a concept called a dominant term. At that time, I also mentioned minor terms. Dominant term, other than the dominant term, we have some minor terms. The question is, can we ignore those minor terms? Yeah. That's the unnecessary details. Okay? To simplify our function representations. All right. Here, let's look at this formula, this property, this formula. All right. If we take a ratio, what ratio we want to do the comparison? We compare these two ratios. Left-hand side, we double the problem size, 2n, double the problem size. The problem size becomes 2n. Okay? Yeah. Then we know the algorithm response time should be larger, right? Yeah. You increase the problem size, usually in general, the running time should be longer. In general, yeah. Although there could be exception, yeah, but here we look at the general case. Yeah. All right. Yeah. Then the ratio, capital T of 2n over capital T of n, approximately equal, yeah, because if you use this formula, that little COP constant will be canceled out. Numerator, little COP, denominator, little COP will be canceled out. After the cancellation, the constant cancellation, okay? Constant cancellation, yeah. Yeah. Here we assume the positive constant, right? Yeah. Yeah. Because based on our assumption, yeah, based on the assumption here, it must be a positive number. Okay? So we can do cancellation, positive number. Okay, yeah. So approximately equal right hand side, capital C of 2n over capital C of n. Yeah. So we have this observation. What does this approximate equality tells us? From this formula. So we can see these two functions, t function and a c function, they have the same increasing rate, right? Because when you double, then you look at the rate. Yeah. So we measure the increasing rate using this way. Okay? The problem size double, then we want to look at the ratio of the function when the problem size is double. That rating we can use to measure how fast a function is increasing. Okay? Yeah. So if we use this view to see the increasing rate, yeah. So these two functions, they have the same increasing rate. Okay? Yeah. Same rate of increasing. Okay? Yeah. In this way. Then let's go back to our characterization, original question. If two functions have the same increasing rate, can we put them in the same category? That's the way we want to do the characterization. Yeah. Yeah. It's a nice characterization. Yeah. We'll put those functions with the same increasing rate in the same category. Okay? Yeah. That's the conclusion. From the observation of this formula, we get that conclusion. All right? Yeah. Functions with the same increasing rate. How do you describe increasing rate? We use this way to describe increasing rate. Put it in the same category. Okay? Yeah. All right. Yeah. All right. So that's the first step. Okay. All right. Yeah. Yeah. All right. Then, this time, growth function. Yeah. Let me talk about this growth function concept. What is the major term in an efficiency function? Yeah. All right. We need to review, we need to recall our dominant term concept. Then growth function. These two concepts are related. So here I do the comparison to let you see the difference. So what's the, difference? Yeah. So let's look at our selection sort. We have the efficiency function from the selection sort. This is the efficiency function of the selection sort. All right. Let's expand. So this is a polynomial. Let's represent this polynomial in terms. Yeah. We have two terms. The first term, 1/2 times n squared. The second term, minus 1/2 times n. There are two terms. Yeah. So let's use our dominant term concept we introduced before. What is the dominant term in this function? The first term. First term is the dominant term. We can easily see it dominates the second one. Dominates in a certain way. Certain way. Yeah. Next time I use calculus to show you the meaning of dominance. Okay? Here, you see, when n is large, the first term is much larger than the second term, right? When n is very large, the first term is much larger than the second term. That's the dominance. Okay? All right, the dominant term. The whole term is dominant. All right. Next, what is the growth function here? In this efficient function, we want to define growth function. Growth function. So the growth function here is, so here the dominant term, to see that we take the limit, okay? Dominant term over that minor term, first term over the second term. If you take the limit, when n goes to infinity after cancellation, 1/2 cancel out. So n squared, bottom n cancel out. So you get a limit where n goes to infinity, the limit of n, it's infinity. So the ratio of the first term over the second term, when n goes to infinity, it's infinity. Can you treat that infinity ratio as dominance? Right? Infinity ratio, the ratio goes to infinity when n goes to infinity. That's definitely dominance, right? Yeah, dominance. So we use this calculus way, the limit way, we can see the dominance in this way. Yeah. All right. Then, when we talk about the growth function, so we simplify the dominant term another round. Dominant term contains that 1/2 coefficient. That 1/2 coefficient, remember, the little c op is canceled out in our previous slide. When we do the characterization, we can ignore that little c op constant when we do characterization. Okay? Yeah. Because for the function with different coefficients, we can put in the same category, right? Yeah. The function with different coefficient, we can put in the same category. Okay? So here, this one half constant, if we want to make the function simpler, we do not need to include 1/2 constant. So we remove that 1/2. We make the coefficient 1. That's simpler. So this n squared we call a growth function. Another round simplification. So on top of the dominant term, we do another round simplification by replacing the coefficient of the dominant term by 1. Make the coefficient 1. Or replace the original coefficient by 1. So we get a simplified term. So that function we call the growth function of this algorithm. Okay? Yeah. So you can see these two concepts closely related, but the difference is pretty small. The difference is just a constant.
This is that for the function, for the dominant term or?
Only dominant term. Yeah, we don't look at minor term. Yeah, because ratio, infinity, you ignore that minor, little, tiny quantity. Yeah. So, all right. Yeah. All right. So next time we do the comparison between method 1, method 2 of that element uniqueness problem using calculus. We do comparison. Okay? All right. Yeah. So let's stop right here.